how loss in transmission lines affects sinusoidal signals. I promised we'd revisit modeling loss and dispersion once we put sine waves on transmission lines, and that time has come. We can take a closer mathematical look now because the analytical representation of our wave makes the math easier. Our strategy is to figure out how the voltage divider in the RLGC differential wire model changes the voltage of a differential, and then use that to form a differential equation that describes changes in the line voltage with position. To make the math easier on that, we're defining two variables to simplify algebra. We're letting little z equal r plus j omega L, and little y equal g plus j omega C. We set up our voltage divider equation here. Like before, we represent our shunt elements as 1 over admittance, and we put the shunt elements in parallel with Z0 to represent the impedance of the rest of the line. After that, we do a couple of steps of exhausting algebra. Pause the video and do them by yourself if you'd like to keep up. The one notable step in the algebra is canceling out the ds squared term, because a differential squared is really small. This step is sometimes called ignoring a second order term, or taking the equation to first order. Finally, we round out this page with a bit of factoring. Picking up where we left off, we can take advantage of the fact that ds is small by using a binomial expansion of our equation like this. Then we remember our expression for z0 and observe that it can be expressed in terms of z and y. And we substitute that into our expression to get something tractable. We can move some terms around to reveal a derivative in the limit as ds goes to 0. Whew, that was a lot of work for a rather simple equation at the end of the day. This is a first-order differential equation, so you can solve it by separating variables just like a time constant or an exponential growth equation. The result is that some initial voltage values v of 0t gets scaled by an exponential as you move along x. I chose to represent this in terms of initial voltage at x equals 0 because it makes for a clean equation, but you could write this equation for any x equals x0 on the line and scale exponentially from that spot. The constant in this equation is just some initial condition on the transmission line. Before we leave this slide, I want to re-emphasize the main takeaway. We've found a really useful equation. This last equation lets us find voltage anywhere on a transmission line if we know the voltage at one spot. Specifically, we find voltages at other parts of the transmission line by scaling our one known voltage exponentially. We need to look closer at the exponential scaling factor we've identified to see what causes attenuation and dispersion. First, we're going to rename it because square root of zy is a mouthful. We call this exponential scaling factor the propagation constant and give it the symbol gamma. We also note that it can be a complex number, so we often express it as alpha plus jk. If we substitute alpha plus jk into the expression from the previous page, we find something interesting. Alpha, the real part of gamma, causes attenuation. It makes signals get exponentially smaller with distance. K, the complex part of gamma, just looks like it adds phase with distance. That's the exact same thing that the wave number k did when we looked at the infinite transmission line, and that's because this k is the wave number. We still see phase advancing as we move along lossy transmission lines, and the k part of the propagation constant reflects that. I need to add a few naming convention notes about propagation coefficient. First, sometimes the symbol beta is used for the complex part of the propagation coefficient instead of k. Second, sometimes alpha is expressed as the tangent of an angle called the loss angle. Back on track. We can substitute expressions for z and y into our expression for gamma, and then do some truly heinous complex algebra to get expressions for alpha and k in terms of r, l, g, and c. These expressions are horrendous, but they reveal something important, specifically that k varies with omega in the general case. We don't have time to get into it here, but the delay of a sinusoid of some frequency through a system, which is called group delay, is given by the derivative of phase with respect to frequency. Having a value of k that depends on frequency gives rise to different delays at different frequencies, which is how you see dispersion in a line. Finally, we can simplify our expressions for the propagation constant quite a bit in a few special cases. The lossless condition is predictably easy. Note that k is equal to omega over v in this condition, and in all the conditions on this page, because v is equal to 1 over the square root of LC. We can find simple expressions for alpha in the low loss and heaviside conditions too, which is nice. Note that alpha has units of inverse meters, which you can see because it's given by ohms per meter divided by ohms. That's because alpha gets multiplied by a distance to form the argument of an exponential, and exponential arguments need to be dimensionless. Inverse meters is a funny unit, and you won't see it on data sheets. Instead, alpha is commonly expressed as dB per meter to make calculations easier. So in summary, the propagation coefficient is used to find voltages at different places on the transmission line from voltages at a known position. And this equation shows that relationship, and also that the propagation coefficient gamma can be broken into real alpha and a complex beta or k part. Attenuation comes from the real part of the propagation constant. Dispersion comes from phase depending on frequency, which leads to different group delays for different frequencies. And the special conditions that we talk about, low loss, heavy side, and lossless, don't have any dispersion, and we'll mostly use those in this class.